What happens when a router loses its base path? How does it discover another route without someone manually reconfiguring the network? Well, that's where OSPF comes in. OSPF is a link state routing protocol that allows the routers to learn the network topology and independently calculate the shortest path to every destination. First, neighboring routers discover each other using OSPF packets. Once they agree on important settings, they form a neighbor relationship called an adjacency. The routers then exchange link state advertisements or LSAs. An LSA describes information such as routers, links, connected networks, neighboring routers, and the path cost. Each router stores those advertisements inside its link state database or LSDB. Routers within the same OSPF area should build an identical view of the network. Every router runs the shortest path first algorithm against its own LSDB. This calculates the shortest path tree and determines the best route to install in the routing table. When the topology changes, OSPF floats updated LSAs. The routers update their database, rerun the SPF calculation, and quickly select a new best path. So in this video, we're going to build this process practically. We'll configure OSPF neighbor relationship, examine LSAs and LSDB, work with OSPF areas, and verify how exactly OSPF chooses its best path possible. Now the topology is ready. I'm going to use the pre-built lab to save us a lot of time. I already made a separate video showing how to build this entire topology automatically using Python. If you haven't seen it yet, you'll find the link in the description. That script configure the basic settings and so you don't have to write and waste a lot of time. If you're preparing for CCNA or you build labs frequently, automation like this saves us a huge amount of time. Now, all we need to do is configure the IP addresses and OSPF. You notice that it's automatically starting all these devices for us. Now, just to give you an idea of how much time the automation saves us, I'm going to manually add these network labels to the topology. This is not a configuration step. I'm only writing the network addresses so you can see the time it takes to do these small repetitive tasks manually. For R1 side, I'm going to add the LAN network address and same for the R4. Even something as small as labeling networks take time when you're building the large topologies. Now imagine manually creating dozens of routers, interfaces, and configurations. This is where automation becomes extremely useful and can save us a lot of time. Then I'm gonna say no to initial configuration dialog to all the routers. One recommendation before we start. In GNS3, go to the view and enable show interface labels. This makes it much easier to identify the correct interfaces while you're configuring the routers. Let's go ahead and configure our IP addresses. We're gonna go to R1, enable config terminal, and choose the interfaces and put IP addresses with masks. Now, you'll notice that all of the point-to-point links between R1, R2, R3, and R4 uses /30 subnet masks, while the last connected to the PC is using /24 subnet mask. This isn't necessarily the most practical addressing schema for every network, but I choose it intentionally because later in the video I'll explain how OSPF uses wildcard masks and why the wildcard mask changes depending on the subnet mask. Using both /30 and /24 network mask makes the concept much easier to understand. After configuring each router, always verify your work with the show IP interface brief and never assume your configuration is correct. Always validate it before moving on. I'm going to speed up this part, but I'm leaving it in the video so you can still see exactly what I'm typing. Now let's configure the PCs. We will assign the IP address, subnet mask, and default gateway. In GNS3, you can either enter the full subnet mask like 255.255.255.0 or simply write /24. Both methods work perfectly fine. I'm going to show you. Now it's time to configure OSPF. We'll enter router OSPF 1. 1 is locally significant, meaning it only identifies the router process on this router. It does not have to match on every router for OSPF neighbors to form. Next, we'll configure a router ID. The router ID is simply a unique identifier for each router inside the OSPF domain. It doesn't have to match any interface IP address, but every router should have a unique router ID. Now we'll advertise our network, for example, network 10.0.12.0, 0.003 area 0. You might be wondering why we're using 0003 instead of 255, 255, 255, 252. That's because OSPF uses a wildcard mask, not a subnet mask. A wildcard mask is simply the inverse of the subnet mask. For example, /30 is equal to 255, 255, 255, 252. Wildcard is 0003. Likewise for /24. It's 255, 255, 255, 0. Wildcard is 0000255. OSPF uses wildcard to determine which interface should participate in the routing process. We will advertise every connected network this way. Now, once we're done with the OSPF configuration, we run show IP OSPF neighbor to check if there is neighbor, and then show IP OSPF database to validate our work if it really worked or not. It's really important to validate every step. Now let's move on to the second router and do the exact same OSPF configuration down there as well. You'll also notice that I'm placing every network into area 0. I'm doing this because this lesson focuses on learning the basics of OSPF. In large enterprise networks, you might have multiple areas like area 1, area 2, or area 10 to improve scalability. However, every multi-area OSPF network requires a backbone area, which is area 0. For this lab, using a single area 0 keeps everything simple and much easier to understand. After configuring each router, always verify your OSPF neighbor. Run show IP OSPF neighbor. If you don't see the expected neighbor, stop and investigate before moving on. One habit that separates good network engineers from beginners is validating every step instead of assuming everything works. Now we configure our tree the same way. We're gonna give him router ID 3.333, and then we're gonna verify that it has 2 neighbors. Now let's test the connectivity. The ping fails. Instead of deleting everything and starting over, let's troubleshoot it. This is actually one of the most valuable part of networking. Anyone can follow a configuration guide. A real network engineer knows how to find and fix problems. Let's isolate the issue. Can we reach R4? No. Can we reach R2? Yes. That tells us the problem is somewhere along that path. Let's check the OSPF configuration. Here we can see that one of the connected network wasn't advertised on the OSPF. If a network isn't included in the OSPF configuration, OSPF wouldn't advertise it, and other routers wouldn't learn how to reach it. After adding the missing network, let's test it again. We're still seeing another issue. Let's look carefully. The line uses /24 subnet mask, but the wildcard mask was configured on 0003. That's only correct for a /30 network. For a /24, the wildcard mask must be 0002255. Even a small mistake like this prevents OSPF from matching the interface correctly. After correcting the wild mask, let's test again, and now everything works perfectly fine. Another configuration error. There's one more issue. Looking back at the interface configuration, I accidentally configured the wrong subnet mask on one interface. When you're typing quickly, mistakes happen. That's why verification is so important. Rather than memorizing commands, learn how to read your configuration and understand what every command does. Now let's look at the routing table. We'll use a show IP route 192.168.21. So notice that R1 has two equal cost paths to reach the destination. Because both paths have the same OSPF cost, OSPF performs equal cost multi-path, also known as ECMP. This means that the router load balances traffic across both paths instead of sending everything through a single link. Now, let's change the OSPF cost. Now, let's go to interface fast Ethernet 1/0. I'll increase the interface cost to 10 using IP OSPF cost 10. Now, let's check the routing table again. Notice that OSPF no longer load balances traffic. Instead, it chooses the path with the lowest total cost. That's OSPF from start to finish. We configured the routers, phone, neighbor relationships, advertised networks, learn how wildcard masks work, troubleshoot real configuration mistakes, and even saw how OSPF performs load balancing and chooses the best path. I intentionally left the troubleshooting in this video because that's where the real learnings happens. In networking, you're not paid just to configure devices. You're paid to understand problems and solve them. If this video helped you understand OSPF a little better, give it a thumbs up. It really helps the channel grow. If you're a student or studying for CCNA or want more networking labs like this, make sure you subscribe because we've got a lot more coming. Thanks for watching. It's your boy Yusuf. See you in the next one.